Kia ora and welcome to video 24 in the series Delightful Differentiation, our penultimate video in the series. Today's video we're going to diverge a little bit outside of NCEA mathematics into an area of maths that's more commonly seen at university. However, the maths is valid for scholarship examinations because you can use NCEA level 3 maths to solve the problem. So the suspense is real. Here we go. What are we going to do? We're going to look at a Taylor series. The Taylor series of a function at x equals a is given by that beast of an equation. It's actually fairly straightforward. It's a sum. This here represents the derivative, or the nth derivative evaluated at a, so differentiation skills, dividing by n factorial and timesing by this bracket here to the power of n, which is just a polynomial. F of n of a denotes the nth derivative. I've already said that. The nth Taylor polynomial, P n of x, consists of the first n plus 1 terms of the series. So this series here goes to infinity, but if we were to truncate it and look at a partial sum, that partial sum, if I stopped it at 7, for example, which I need to do for this question, that there would be a polynomial of degree 7, because that highest power there will be 7. It will have 8 terms though, because n equals 0 is our starting point, and that is a constant. So, just like a cubic, when you write out a cubic, it actually has 4 terms. A quadratic has 3 terms, and so on. Okay, this picture kind of shows you what's going on here. We've got the function sine of x approximated with this polynomial. It's pretty good for values close to where you're approximating, so in this case x equals 0, but it's not so good outside a range of x, which is called an interval of convergence. Okay, find the equation of P7 of x for the function sine of x about x equals 0, and then hence or otherwise find the 15th derivative of sine of x cubed. So good luck with the problem, something a little bit different. Hope you enjoy it, and we'll see you after the intro music for the solution. Okay, so let's find the Taylor polynomial P7 of x. We need to get 8 terms out of the series because we start at 0, the constant term, and we want to go up to the 7th power, degree 7. We need to evaluate all the derivatives at x equals a, our x is 0, and then kind of work out what the sum is doing. So I've saved us a little bit of work here. Jokes, I recorded this and then stuffed it up and I couldn't be bothered rewriting it. So here is the function sine of x all the way down to the 7th derivative, evaluated at x equals 0. Now we need to substitute that in, divide it by n factorial, and then multiply by x minus a, but a is 0. So okay, we've got the sum from n equals 0 to 7 of f of n evaluated at a. Remember, that means derivative of f, the nth derivative evaluated at a, divided by n factorial, all multiplied by x to the n, not x minus a because we're at 0. This is actually called a Maclaurin polynomial because it's 0. It's a special one. Okay, so first derivative was 0. Sorry, not the first derivative, the 0 derivative of the sine of x function is the 0. Then we've got cos x, this is n equals 1. So we've got cosine of x, no we don't. Cosine of x evaluates to 1, so we've got 1 over 1 factorial. I'll just write it out like this so that we can see the pattern. X to the power of 1. We don't need the second term, n equals 3. So it's going to be minus 1 over 3 factorial times x cubed. N equals 5 comes in. That's plus 1 over 5 factorial, x to the 5. And then the last term we need, n equals 7. It's minus 1 over 7 factorial, x to the 7. Look, we could evaluate those factorials. So obviously x is the first term, 3 factorial is 3 times 2 times 1, so we end up with minus a 6th x cubed. 5 factorial, 5 times 4 times 3 times 2 times 1, so 120, x to the 5. And then lastly, 7 factorial, 7 times 6 times 5 times 4 times 3 times 2 times 1, which is 42 times the number 120 there. And that comes out to be 5,040. It's a very small term, but it is being multiplied by x to the 7, which blows up quite quickly. So it makes sense that the coefficient there is quite a small one. Just going back to the picture and the problem that it's shown there, you've got the sine x graph in blue, and you've got this polynomial there, which is perfect pretty much around the origin, right? It has the same function value, the same derivative, the same second derivative, etc. But it starts to diverge after a certain point. If you go on to study mathematics at university, some of you may have already seen this, you get this kind of radius of convergence idea. If we have an infinite number of terms in that Taylor series, then the red and the blue will be in sync. But of course it's not. It's only 7 terms in this polynomial that we're using, so therefore there is some divergence because sine x is obviously not a polynomial. Let's use infinite terms. Okay, so that's our approximation for sine of x. We could turn this into an approximation. And then the second question asks us to find the derivative, the 15th derivative of sine of x cubed, evaluated at x equals 0. We've got to find this link, or otherwise basically is suggesting you differentiate the thing 15 times. Good luck. The first derivative is easy, it's chain rule, then you're going to need product rule, and then it's just going to blow up. So we're going with the hence option, as you most likely do in exams. The 15th derivative is an interesting one because we've actually only got a polynomial of degree 7. So we kind of need to find the link here. And the link is the fact that this is sine of x cubed, not sine of x. Look, we could go back via the Taylor series and find a Taylor polynomial for sine of x cubed, but that would require differentiating sine of x cubed. And we're trying to get around doing that. So sine of x cubed, in fact, we just use the sine of x function, and we replace x with x cubed. So sine of x cubed is going to be approximately x cubed minus 1/6 of x to the 9, because x will be x cubed and we're cubing it, plus 1 over 120 x to the 15 minus 1 over 40 x to the 21. Okay, now what happens when we differentiate this 15 times? Well, x cubed becomes 3x squared, becomes 2x, becomes 2, and then it becomes a constant. And then the constant disappears. So that's the key in all this. If we differentiate this 15 times, quite a few of the terms, in fact, the first 2 terms disappear. The last term is not going to disappear. It's going to be x to the power of something, and then we're going to sub in 0 into it. So these 2 terms here will disappear. This term here will be 0. First 2 terms disappear, and last term is 0 when x equals 0. So we just need to consider what happens with that third term. So we're going to get 1 over 120 times 15 times 14 times 13 all the way down to 1. You think about what happens with the power. The 15 comes down the front, it becomes a 14. The 14 comes down the front, it becomes a 13. All the way down to a single power comes down the front, and the power drops to x to the 0, and x to the 0 is a constant of 1. So if you want to write this in factorial form, you can write 15 factorial over 5 factorial, bearing in mind that 120 was 5 factorial, or you evaluate that using a calculator or your knowledge of factorials, and you get an answer of 10 billion something or other. I think we'll just leave it in factorial form.